Hi, in this tutorial, we are going to be discussing two questions. Question one is the C code is already given, and you can try it out and see how changing the logic operators plays around with all the bit manipulation of the data that we're dealing with. Okay, so I'll leave that to you to try. So let's look at question two. In question two, you are asked to do swapping, and basically we know that swapping is a standard algorithm using a extra variable. So in this case, for example, this is t. So all I need to do is, given two variables a, okay, and b, okay, when I want to do a swap, okay, I create a third variable, temporary slot, and then what do? I take a, put into t, put b, take from b, put into a, and then from t I transfer back into b. So that is what your traditional algorithm does. Okay, but the only sort of drawback with this is that it creates a additional variable t here. Okay, and in this question you are asked how you can go about doing it without creating an additional variable. Okay, so the key thing is we do not want to create any additional variable. Now, if you Google for this, obviously you'll get the answer straight away, and we know this works, but let's just convince ourselves that this actually works. Okay, so let's give ourselves some data points here. Okay, so let's say I say that variable a is given this value 1010 1100, and I say variable b. Okay, and I say variable b and variable a, maybe to clarify, it is the data that I'm pointing to, the actual data, and b I give it as 0110 1001. Okay, so let's look at what is happening at a step by step. So in the first step, what we're doing is we are taking a exclusive OR with b and putting back into a. Okay, so I'm going to take this operation, asterisk a is equals to asterisk a exclusive OR with asterisk b, and I'm going to call this a step 1. Okay, and what is the result? Okay, so let's look at the result that I get when I do a exclusive OR operation between these two data points. So 0 1 I get 1, 0 0 is 0, 1 0 is 1, 1 1 is 0, 0 0 is 0, 1 1 is 0, 0 1 is 1, 1 0 is 1. Okay, so in case you're not very sure, exclusive OR operation, the truth table basically looks like this. Okay, so if I take x, y, okay, and I take the output z 0 0 0 1 1 0 1 1. Okay, and the easiest way to remember exclusive OR is, as long as the two inputs are different, the output is a1. When the two inputs are the same, the output is a 0. Okay, so that is the easiest way to remember the exclusive OR operation. So that is the first result that you get, okay, from the first step. Now let's look at the second step. So in the second step, what am I doing? I'm doing this. Asterisk b equals to asterisk a exclusive OR with asterisk b. So now you have to remember that this asterisk a is referring to the current a, which is the a after I completed step 1. So now I'm going to do the exclusive OR operation, okay, with the b that I currently have. So basically I'm doing this operation, this exclusive OR with this. Okay, now what is the result that I get? Okay, 1 and 1 is 0, 0, 0, 1 is 1, 1 0 is 1, 0 0 is 0, 1 0 is 1, 1 1 is 0, and 0 1 is 1. Okay, and what do you see here? You see that right now, actually, okay, the actual a value has now been transferred over to b. Right, has now been transferred over to b. So this is b at step 2. Okay, so you can see that right now the a value, the original a value, has already been transferred over to b. Okay, now let's complete the last step. Okay, so the last step, step 3, is to say asterisk a equals to asterisk a exclusive OR asterisk b. Okay, so what I'm doing now is the current B, which is this, and I'm going to exclusive OR with the current A. So I'm going to do this and this exclusive OR operation. Okay, so let's see the result. Okay, so that is the A from step 3, and what is the answer I get? 1 0 is 1, 0 0 is 0, 1 1 is 0, 0 1 is 1, 0 0 is 0, 0 1 is 1, 1 0 is 1, and 1 1 is 0. And what do you see? This is actually the original B value that has now been transferred to A. Okay, so you can see that by doing exclusive OR 3 times, okay, between the two variables, I'm actually able to do a transfer or exchange of data between the two variables without, okay, so the key thing is without having any additional variable. Okay, so we're not going to go into the mathematics of how this actually is feasible, but from an example, you can see that it actually works. Okay, so this is one alternative way now that you have learned to do swapping without creating an additional variable. All right, so that is question 2. Okay, now let's go on to question 3. Okay, in question 3, you are asked, okay, you're given that you have two variables A and B, and you have mapped them to registers S0 and S1 respectively, and you're asked to implement these two functions. So the first one is A, which is A, B is equals to A percentage 16. Okay, so whenever you see this operator percentage sign, it basically means you're trying to look at the remainder of A after it's been divided by 16. Okay, so let's look at another simple example first. Okay, so assuming that if I say C is equals to D percentage 10, that means I want to look at what value do I get after I take D divided by 10 and the remainder. Okay, so let's assume that D has a value of 92. Okay, then what do you expect? So 92, if I take divide by 10, I will get 90 remainder 2, correct? Okay, so anything that is at the ones, okay, will be retained, and anything more than the ones will be gone. Okay, if I take that D is maybe 157, for example, 157, and I do the same thing, what will I get? I'll get 150, okay, and then remainder 7. Okay, so what am I trying to show you here is when I do a percentage 10, the answer that I get would be in the range of 0 to 9. Okay, so the answer would be the ones position number. Similarly, if I were to do, coming back to the original question here, if I were to do a percentage 16, that is equivalent to saying that the answer that I'm going to get from here would be in the range of 0 to 15. Okay, and 0 to 15 basically means that in terms of a binary representation, it is the last 4 bits of any binary number. Okay, why? Because the last 4 bits will go from 0 0 0 0 all the way to 1 1 1 1. Okay, that is from 0 to F, and F is 15. Okay, so what you can see here is that A percentage 16 will actually what I'm trying to do with A percentage 16 is I'm just trying to retain the last 4 bits of the actual value in A. Okay, same thing over here. If I say D percentage 10, I'm only looking at the last bit, the ones bit. So I can discard the numbers in the tens position or the hundreds position. Same thing over here. If I say A percentage 16, I'm looking at the last 4 bits. And anything beyond that, I do not need to worry about. And how can I do that in MIPS assembly language code? I just need to write an instruction to keep the last 4 bits. Okay, and if you recall from our lecture slides, to keep the bits, okay, I can do an AND operation. Okay, so NI, and what I want to do is the original data is A, and A is in S0. Alright, so S0, I do an AND operation with 15 to 0xF, and the result go into B. Okay, B is S1. So the result go to S1. Okay, so that is the answer. Okay, so this is a immediate operation, and immediate. So I specify the source register. This is the source register. Okay, this is the immediate value, and finally this is the destination. Okay, so that is part A. Now let's look at part B. Okay, so in part B, what are you given? You're given that B is equals to A divided by 8 multiplied by 8. If you recall from the lecture slides, I mentioned that whenever you do a division or multiplication, if you are dividing or multiplying by a number that is can be represented as a 2 power, then it is very convenient because it is equivalent to doing a left shift or right shift. Okay, so 8 is 2 to the power of 3. Okay, that means this operation A divided by 8 is equivalent to saying that I shift right by 3 times, and multiply by 8 is equivalent to shift left by 3 times. Okay, so if you look at it from the data perspective, okay, imagine that the original data in A, okay, is something like this. Okay, 0B, maybe 1, 1, 0, blah, 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 until I look at the last 4 bits, maybe 1, 1, 1, 1. Okay, and if I try to do a right shift by 3, which is this operation, what will I get? Everything will shift right by 3. Okay, and so the last 3 bits will get shifted out, and this one will come here. Correct? So what I will get is 1, then I don't know what is all this. Then since I shifted right by 3, I will have to replace by 3 zeros, then 1, then 1, 1, 0, and so on. Okay, so that would have been the answer after I shift right by 3. Okay, now when I do the left shift by 3, what happens? I will shift back by 3 bits. Okay, so this 1 will come back here. Okay, so 1, 1, 0. Okay, things had dropped. Okay, let me just write this properly here. Okay, so 1, 1, 0. Okay, all the way until the 1 here gets shifted back here, and then I get 3 zeros back here again. Okay, so what do you see happening? You see that actually the whole process is taking the last 3 bits and clearing them to 0. Okay, by doing a shift right by 3, okay, followed by a shift left by 3, I am effectively discarding the last 3 bits of my number. Okay, how do I code that? Okay, in my assembly language, I can say shift right left. Okay, so I'm going to use a temporary register T0 first. Okay, so I'm going to shift left S0 by 3. S0 is the A. Okay, I'm going to shift left by 3 and put into a temporary register T0, and then I'm going to shift left by 3. Okay, so T0 shift left by 3 and put the answer into S1 because S1 is B. Okay, so this is effectively how you can do it. Now, looking at the objective of the operation, which is to clear the last 3 bits, we can recall that we mentioned in the notes that to clear any bits, we can do a AND operation. Okay, we can do an AND operation with 0. In part A, when I want to keep the last 4 bits, I do an AND operation with 1s. If I want to clear the bits, I can do an AND operation with 0. Now, how can I do a AND operation with 0 over here? Okay, okay, let me move this down a bit. Okay, okay, so to do an AND operation with 0, okay, I must take the actual data 0B, for example, this is my data 1, 1, 0 all the way until 1, 1, 1, and I must do an AND operation with 0, 0, 0, 0. Sorry, I want to clear the last 4 bits, correct? So everything else must be a 1, okay, until the last 3 bits must be 0. Okay, so the result, okay, the result of the AND operation would be such that the last 3 bits would be cleared. Okay, so that is what I want to do. And since this is a immediate value, okay, I need to specify it something like this, something like part A. But what is the challenge is, in immediate instructions, the immediate value that I can specify is limited to 16 bits. Okay, but this is a full 32-bit number. Okay, I cannot specify a full 32-bit number as an immediate. I can only limit it to 16 bits. So in MIPS, the way to go about it is to break it up into 2 steps. Okay, the first step is to call load upper immediate T0 with 0xFFFF. And what does this do? Okay, so when I do this, inside my T0 register, okay, so this is the lowest upper 16 and lower 16. So inside my T0 register, I would first load FFFF inside here. Okay, and the lower bits will by default will be 0. Then I do a OR operation of T0 with the value that of FFF8. So what does this do? This one will OR it with 0, 0, 0, 0 and FFF8. Okay, so when I do an OR operation, then the result of this OR operation will be FFFF, FFF8. Okay, and if I look at 8 in binary is 1000, okay, which is the last 4 bits that I want. Okay, so once I do this, basically the value in T0 is the mask that I want. Okay, this is the mask that I want, and with this mask I'm able to keep the 1s and discard the 0. So the last 3 bits will be discarded after I do the AND operation. So I can now do an AND of original value which is in S0 with the mask which is T0 and the answer put into S1. Okay. When I do an AND operation between registers, no problem, because each register itself is 32-bit. Only when I want to do an AND immediate, okay, then the immediate value is limited to 16 bits. Okay, so this is how you can solve part B. So the first way is I can write it with 2 shift operations, or the second way is to do this. Okay, load an immediate value into a register in 2 steps and then do the AND operation. Okay, so that is the explanation for question 2. Okay, so let's go on to the last question in the tutorial. So in this question, you are given some code, okay, and some data here. Okay, let me move this data here a bit. I got more space. Okay, now let's look at the first step. The first instruction says, okay, so let's look at the initial values first. Okay, so you have a register, okay, S1, okay, and S1 has a value initialized to 0, and then you have another register T0. Okay, T0 initial value is 112. Okay, now let's look at what happens step by step. Okay, as we go through these instructions. So we are given that we are going to be executing this set of instructions for 3 iterations. Okay, so that is what the question is given, and we are asked to find out what is the value in register S1 after I complete 3 iterations. Okay, so the first thing is I check whether T0 is 0. So T0 is not 0, so I will not take the branch. I come to the next line. So in this line, this is a load word instruction. So in load word instruction, this is so let me write this instruction here. Load word T1 0 T0. So in this instruction, okay, this is the and you take the value, okay, that T0 has, add with the offset, okay, that you specify here, and this gives me the memory address. Okay, and what do I need to do? I need to go to this memory address and fetch the data and take this data and put it into my register. Okay, that is how a load word instruction operates. So in this case, T0 is 112, add with the offset 0, so and this gives me the memory address. So I go to address 112, take the data. The data is 108. Take this data and put it into my register T1. Okay, so T1 register has now a value of 108. Okay, after that, what do? I do an add operation between S1 and T1. So S1 add with T1 and the result put back into S1. So 0 plus 108, so the value in S1 becomes 108. Okay, next so that was the second instruction. The third instruction says load word from T0 add with 4. Right now T0 is holding 112, the offset is 4. So 112 plus 4 means I'm now pointing to 116. Okay, and take the data from address 116. The data is 124, and take this 124 and put it inside my T0. So T0 is now going to change to 124. Okay, so that is the first iteration. Then I jump back to the loop here. Okay, then I check. Is T0 0? No. Okay, so I don't need to branch. I will go to the next instruction. The next instruction, now is the second iteration. So I will load again from wherever T0 is pointing to. So T0 has a value of 124. Offset is 0. So 124 is here. And I take the content of 124, which is 104, and put it to my register T1. Okay, so from now the register, the value in T1 register will be 104. Okay, then I do the third, the add operation, which is to add S1 and T1, put back into S1. So 108 plus 104, put back into S1. So I will get 212. Okay, so let me write that explicitly here. Okay, so 108 plus 104, which will give me 212. Okay, now I will do the second load operation, which is T0 plus 4. So T0 is currently 124, so plus 4 is 128. So this is the memory address. The content is 100. Take this content 100 and put it inside my T0 register. Okay, so currently I'm here. Okay, the second iteration. Then I jump back to the loop and I start my third iteration. So in my third iteration, again I check T0, is it 0? No, so I exit. Then I come back here. Then what do? I load. So T0 is 100, so I take 100 plus 4. Sorry, I take 100 plus 0. Okay, so in address location 100. Okay, what do I see? I see the content of 120. Correct? So I take this content 120 and I put it inside my T1 register. Okay, next I do the add operation here. Then add operation S1 plus T1. So 212 plus 120, I will get 332. Okay, and then what do? I load word T0 plus 4. So this is T0 plus 4 is 104. So I will take the contents from this, okay, 132, and put it inside my T0 register. Okay, and then I jump back to the loop. Okay, so this is the 3 iterations of the loop. So at the end of the 3 iterations, the value in S1 register is 332. So that is the answer for part A. Okay, so in part B, you are asked to terminate the loop at the 4th check of BEQ. So what memory content must you modify? Okay, so you can see that right now I'm actually at the beginning of that fourth iteration, and in order for me to terminate the loop, this condition must be satisfied. That means whatever content in T0 must be equal to 0. Then I will terminate the loop. Okay, and T0 is pointing to T0 is holding the value that was obtained from the address in 104. Correct? So if the content in 104 is now changed from 132 to 0, correct? Then it means that when I branch back for the fourth iteration of the loop, then this would have become 0. Then I would have terminated the loop. Okay, so that is the answer for part B. Okay, in order for me to terminate the loop at the fourth iteration, the content of address location 104 must be 0. Okay, so this is to give you hands-on experience and understanding on how the load word operations work, how branching works, okay, and how a loop is constructed, okay, within the MIPS programming language. Okay, so I hope this has been this video will help you with your understanding further. So any questions, you can always clarify in class or through the forum. Thank you.